Okay, an asteroid whose mass is 3.7 times 10 to the 7 kilograms is very far away from our solar system and all other gravitating bodies, and is traveling at 200 kilometers per second, roughly in the direction of our solar system. Over time, the gravitational pull of our sun makes the asteroid change course and collide into it. At what speed does this occur? In other words, what is the asteroid speed once it reaches the radius, in other words, the outer edge of the ball of gas that is our sun? And for reference, the mass and radius of the Earth are given there. I guess the first thing to notice is that the only relevant force here is the gravitational force. And by now, hopefully you remember that the gravitational force is nice in the sense that it is a conservative force. That means that there's a potential energy associated with it. So that is something that we will probably need. But before we even get there, let's draw ourselves a picture. We've got the sun that we'll put over here, and let's draw the picture before and after. So here's the sun. And the asteroid, which is coming in from very, very far away. I know this doesn't look very far, but let's suppose that that dot is very, very far from the sun, and it's coming in with some initial velocity, which we're not specifying its direction, but we do know its speed, v naught, and that's given as 200 kilometers per second. Maybe I should go ahead and convert that to meters per second. That's 2 times 10 to the 2 kilometers per second. And I'll end up multiplying that by a factor of 1,000. So 2 times 10 to the 5 meters per second. So that is what's going on initially when it's very, very far away. Then later on, it's crashing in, and so it's just about here. In reality, the asteroid would have burned up. But let's just imagine it has stayed intact and it's got a final speed as it's crashing into the surface of the sun. We can also, if we'd like, to add the radius of the sun here. There it is, radius of the sun. And we have a mass of the sun as well, mass of the sun. That's the symbol that astronomers use for the mass of the sun. And that might be about it. So again, because we have just gravity, Gravity is nice. It's conservative, and therefore it has a potential energy. Let's try to use conservation of energy. So gravitational potential associated with this. Let's try conservation of energy. Now, what does that actually mean? Conservation of energy is a concept that the energy before and after are the same. It is actually used in the form of an equation. The initial energy, whatever it is equal to the final energy. There's only two types to worry about here. Kinetic, that is to say the energy due to motion, and there is potential. So we have some initial potential here, initial kinetic, and that will all be equal to their sum, that is to say, their sum will be equal. Now, we have a gravitational potential, which has an equation form that looks like this. It's equal to minus g times the mass of object 1 times the mass of object 2. Let me write it in this way. It's the mass of object 1, which is the sun, times the mass of the asteroid, which I'll just call ma. And let me label that over here. It's got a mass, ma. And this is divided by their separation, r. And presumably that's the thing we're going to have to think a little bit about. It's r that is changing, and in response, the speed is changing so as to conserve energy. So let's stick this in here. 1/2 times the mass, it's the mass of the asteroid, its initial speed squared. And then add to that the potential energy, which is a minus g mass of sun, mass of asteroid, divided by its initial position, its initial distance from the sun. That'll be equal to 1/2 times the mass of the asteroid, its final speed squared, and then add to that the potential energy at the very end when it's colliding into the surface of the sun. Minus g mass of sun, mass of asteroid, and the final distance. Think about this. The distances are measured from the center of the sun to wherever the asteroid is. This final distance here, that should be the radius of the sun, but we'll do that in a minute. What I notice is that the asteroid mass cancels from this entire equation because it appears in every term. So I'll divide by the mass of the asteroid. I want the final speed, so let me take this term to the other side, in other words, add it. And so at that stage, we have 1/2 v naught squared plus g m naught, or sorry, m initial final position. I'll go ahead and put the final position as r, which is the radius of the sun. Okay, that's what I'm doing here. I'm making that substitution. I'm letting that just be equal to r. And subtract off g, mass of sun, divided by its initial distance, and that'll be equal to 1/2 times the final speed squared. What value are we going to put in for r naught, the initial position? Well, we're told that the asteroid starts very far away. So if you want, you could plug in a number like 1 billion meters or 1 trillion meters. In fact, pick any number you want that's sufficiently huge, and what you'll realize is that because that distance appears in the denominator, the bigger the number you pick, in other words, let this go all the way off to essentially infinity. When you divide by infinity, you get 0. In other words, this entire term is approximately 0. The last step is to multiply by 2 and take a square root. So let's do that. Multiply by 2 and square root v naught squared plus 2g mass of sun divided by r, and take the square root. For those of you who have seen a formula that looks like that before, this actually can be thought of as the initial speed of the asteroid squared plus the escape speed of the sun squared. And in any case, we have all the numbers we need. We have g, which you can look up in a textbook. We have the mass of the sun. We have the radius of the sun, and the relevant speed, the initial speed of the asteroid. This comes out to be approximately 650 kilometers per second.